So in this video, we're going to look at what is known as the source-free RC circuit. But before we go into the details, we want to take a step back and reflect on what we covered in Chapter 7. So remember, Chapter 7 covered the basics of inductors and capacitors. And we called both of those components reactive components because they actually stored energy rather than consuming energy. The capacitor stored energy in an electric field, and the inductor stored energy in a magnetic field. And for both of those components, the relationship between their currents and voltages was actually a differential equation. For a capacitor, the current was equal to the product of the actual capacitor times the rate of change of voltage over time, or I equals C dV dt. Kind of, you notice there, it's hard for me to say it because you usually just keep it in your mind, I equals C dV dt. And because of that duality between electricity and magnetism that we spoke of, we can find the differential relationship that governs the IV relationship for an inductor by simply swapping the currents with voltages, or the I's with V's, and the capacitor with the actual inductor value. So if I equals C dV dt, then for an inductor, V equals L di dt. So since each of those are individually differential equations, or ordinary differential equations, ODEs, meaning that there's only a derivative of one variable within the differential equation. When we actually place them into circuits, the equations which we can derive using the circuit laws that we've discussed so far in order to determine what's known as the instantaneous or the time domain response of that circuit, that is going to be a differential equation as well. So what we're ultimately going to have to do when we're solving circuits that involve inductors and capacitors in the time domain is solve differential equations. So if you haven't seen differential equations before, that's okay. We're not going to go into too much detail in this class, but one thing that you need to know is when you're thinking about the solutions of differential equations, you can decompose them into various decomposition frameworks. So the first actual bullet point that we have there decomposes the total response or total solution to a differential equation in terms of its steady state response, which is time independent, and its transient response, which is time dependent. The more common one that we're going to use in this particular chapter is viewing the total response of a differential equation as consisting of the sum of the natural response. The natural response is the response of the circuit due to the energy that's stored as expressed by the initial conditions only, and the force response, which is the response that's due to the actual source that's connected to the circuit. And that force response, of course, will dominate the behavior of the system over long periods of time versus the natural response, since all of the systems that we're going to look at in this chapter, RC and RL circuits, have a resistive component which can kind of burn off that original energy that's stored in the circuit. That will only be observed over the initial period of time in the circuit. So the complete response, of course, is simply going to be the sum of either of those two components, either the steady state or transient, which we won't look at, or the natural and forced response. So when you think about a source-free RC circuit, here is a schematic for it on the right. It's pretty basic, right? Just a resistor and a capacitor connected together. They're both in series and they're in parallel. And there's only one voltage to define, right? It's the voltage across both of these components. So how can we develop an ordinary differential equation which describes the actual voltage across the capacitor, which is the only voltage in this circuit? Well, one way that we can do it is we can just write the book, and I did it the way of the book initially, and then in latter examples, I kind of simplify it a bit. They actually discuss enforcing Kirchhoff's current law at that node. And that just means that the current that comes in has to equal the current that goes out. So if you think of the current coming out of that node, that's going to be the current pushing down through the resistor. It is going to go from high voltage to low voltage. So it follows our passive sign convention. So that's just going to be actually V divided by R. So that's the equation on the right side for the current coming out. And then for the current coming in, of course, that's going to be the current coming off the capacitor. Notice that relative to this voltage convention, it's actually going from low to high. So that's why the negative is there. And remember that the differential equation that governs the current for an actual capacitor is that I equals C dV dt. So this is the differential equation that governs the solution to this actual circuit. Minus C times dV dt equals V divided by R. So we can actually manipulate that and get it into a more conventional form that you may recognize, particularly if I just move the minus C over to the other side. What I see is that the solution to the circuit is such that the rate of change of the voltage with respect to time is simply proportional to the actual voltage itself. So you know a function that exhibits that type of behavior, namely exponential functions. When you take the derivative with respect to time, you just get the individual function back. The exponential function is called an eigenfunction of the first order derivative operator, which just basically means, for those of you that have seen linear algebra with eigenvectors, when you place them into an operator, the individual input is maintained. So that scaling factor -1 over RC, as we'll see later on in this chapter, is varied behavior with respect to setting the timing dynamics of the response of this circuit. So how can we actually solve this differential equations? And to be frank with you, engineers never solve differential equations. We always rely on either transform domain techniques for kind of relatively novel differential equations or numerical techniques. The amount of differential equations that can be solved using these traditional approaches and framework in time is so limited that it's just not very practically useful. But it's good to go through it as an exercise and actually look what is going on. So these type of simple differential equations, for those of you that have had the course before, you probably know that the way that they can be solved is by separation. And that means getting all instances of one variable on one side of the equation and all instances of the other variable on the other side. So in this case, that will be dv divided by v, and then we'll move the dt to the other side. Now, the thing I want to emphasize is this is going to get a little bit tricky and hand-wavy versus this form of the differential equation is very interpretable. You're looking for a function that when you differentiate it, you get something proportional to itself. That's just an exponential function. But how do you show it through separation of variables? Well, if you move all your terms involving v to one side and you move all your terms involving t to the other side, and you replace that t by a dummy variable tau, because you're actually going to be integrating, the book calls it over voltage and time, but really you're just integrating over time from 0 up to whatever point of reference you want in order to define an expression for the voltage at any point in time. So again, the reason that you're introducing this dummy variable is you want to integrate up to your actual variable t in order to get an expression for v of t. So when you take the antiderivative of basically dv divided by v, or remember your antiderivative of 1 over x dx is just the natural log function, versus on the right side of this equation, when you take the antiderivative of d tau, that's just going to be tau. And remember that even though the reason the book refers to it as integrating over both voltage and time is this v here is assumed to be a function of time. So here in the actual variable, it would be represented by tau. So really, when we take that antiderivative, it's not just ln of v, it's ln of v of tau. That v is a function of tau. And you're evaluating it from the upper bound of integration, which is t, to the lower bound of integration, which is 0. So that's the antiderivative that we're evaluating on the left. On the right, we're just evaluating the antiderivative, which is tau. Of course, on the left here, when you evaluate this at t, you get ln of v of t. When you evaluate it at tau equals 0, that's just ln of v of 0. Typically, your text in this section is going to define the initial condition as just capital V sub 0 here. And then that's just like a given in this case. When we do force responses, we'll see that that typically corresponds to the actual value of the source voltage in the circuit, but there is no source voltage in the circuit. That's just a defined initial condition, a symbol for it. And here on the right side, when we evaluate tau equals t, we get this term. And when we evaluate subtract away tau equals 0, that goes away. Now we can solve this for an expression for v of t, which is what we want. We basically take an exponential function of both sides. Remember, when you take exponential of the natural log of something, they're inverse functions, so they basically undo themselves or go away. And if you manipulate that and solve, you get the expression that we knew to be true, namely this voltage over time in that circuit is just going to be whatever the initial condition is with a decaying exponential function. And the rate of decay is going to be determined by this parameter r times c. And as we're going to see a little bit later on in the course, that's actually referred to as the time constant. So if you think about it, that was a lot of actual just symbol manipulation and work, but it wouldn't have even been possible if we wouldn't have had a differential equation where we can separate the variables. So really the more general approach, as I was kind of referring to earlier, is if you notice you have a first order differential equation, because of that property of the exponential functions, you can kind of rely on the fact that the general solution to those equations is typically just going to be an exponential of the form some unknown amplitude and then some unknown parameter s within the actual argument. So the actual process for determining how the value a and the value s are determined is shown in your textbook. Basically, if you go back to the ODE and you plug in, just guess, a equals e to the st, and you take a derivative and you set the two sides equal to one another, you can find that the actual value of s is just going to be -1 over RC, And then when you enforce that initial condition, so this portion just comes from plugging into the actual equation. When you enforce the initial condition, you see the A is equal to V naught. So oftentimes when you're doing these examples, it gets like really confusing unless you just look at, when you're doing the lectures rather, it gets very confusing unless you look at some example problems. So let's look at some. This is what are we referring to it as? A source-free RC circuit, because it's just a capacitor and a resistor, nothing is attached. So basically what goes on in this circuit is if there's some initial energy stored on the capacitor, from that point in time at which that energy is stored, the voltage will decay exponentially as that energy is eventually consumed in the resistor. So what we want to find here is the time where the voltage decreases to half of the voltage at time t equals 0, which is just the initial voltage. So let's actually take a look at that. And I apologize, I have to pull up my .cam here. Sorry about that. Is the name of the function. 9:42 at night. I've been working since 5:30 this morning, so apologies for that. I know a lot of you have tough schedules too, so we can all relate to one another. So there's the original schematic that we were given, and what we want to find is the time such that the value of that voltage is just its initial value divided by 2 or in half. So remember, in general, for a source-free RC circuit, the voltage at any point in time is just going to be the initial condition multiplied by the exponential function with an argument of minus t over RC. We have some specific values of R and C, namely if we multiply these values together, 2 times 6 is 12, kili is 10 to the third, micros 10 to the minus 6. So in total, that's just going to be 12 times 10 to the minus third seconds, or 12 milliseconds. Important thing about this product, if you trace through all of the dimensional analysis of the unit, this is actually a quantity that's measured in time, which is not surprising because the t that you're plugging in is going to be in time. So really what this is doing is it's normalizing the t in terms of, as we'll eventually see, this RC is called the time constant of the circuit. So we know the value of RC, it's just 12 milliseconds. Notice here, when I rewrote the expression, I just said in our case, V of t is whatever the initial value is, times e to the minus t divided by 12, as long as t is in milliseconds. Now, what do we want to do? We want to find the value of t such that this is the value of the voltage. And we want the value of the voltage to just be V naught over 2. So if V naught over 2 equals V naught e to the minus t over 12, you can cancel that V naught. And basically what you're looking for is the t that makes e to the minus t over 12 1/2. Well, how would you find that? You're trying to solve for a t that's in the actual argument of the exponential function. So you need to take the natural log of both sides. When you take it of the left side, natural log of a half is just a number. When you take it to the right side, natural log of the exponential function is just going to give you the argument, minus t over 12. Solve that for t, basically multiply both sides by negative 12, and what you will find is that it will take 8.32 milliseconds in order for that, in this circuit, for the voltage to reach half of the original value. And we'll have some rules of thumb a little bit later on in the chapter, namely since the time constant is 12 milliseconds, you will know after watching all the videos how much you could expect the initial voltage would decay to in 12 milliseconds. And what you'll see is that decay is more than half. So not surprising that this quantity is 8. So let's look at the next example here. We're given the initial value of the voltage in a source-free RC circuit along with the resistor value. And what we want to find is the value of C such that the voltage at 250 microseconds takes on this value. So it's decayed from 10 volts to 5.215 volts. What is the value of the capacitor to make that happen? Intuitively, we know it's dependent upon the capacitor because we're given a resistor value, and we know that the product of these two things, the R times C, dictates the time dynamics in the circuit. So we want to find C such that the value of the voltage at 250 microseconds equals this actual value. So remember, in general, for any source-free RC circuit, V of t equals V naught e to the minus t over RC. What do we know? We know the initial voltage is 10 volts. We know the resistor value is 100. So if we plug those things in, what we're looking for is the value of time such that V of t equals 5.215. So it's going to be the same thing as the last problem. It's just basically manipulating your exponential expressions to solve for this t. Divide both sides by 10, or if you want, simplify the denominator first. 250 times 10 to the negative 6. When you divide by 100, that's just going to decrease this by 2 orders of magnitude. So it's minus 250 times 10 to the minus 8. Don't forget, you still got your capacitor value in the denominator. Divide both sides by 10 to just get a single constant over here on the left. When you divide by 10, of course, you just shift the decimal one place left. So this is going to be the natural log of whatever that quantity is, is equal to, when you take the natural log of the right side, exponential goes away because they're inverse functions. Just solve this for c, which basically means multiply both sides by c, and then divide by this. So you see c is equal to that quantity divided by ln of 0.5215. That comes out to be 3.84 microfarads, or 10 times 10 to the negative 6 farads. So last problem, much more interesting. Find the voltage V in the following circuit at 200 microseconds. So this is the first example of a switch circuit that we'll be looking at. And basically what had happened was, we're assuming this voltage source was driving this circuit up until our reference point of time, which we're calling 0. And at that point in time, we open the switch up. And basically all that's going to happen is whatever energy is stored on this capacitor is going to be dissipated in the resistors in the actual source-free response. So let's look at how we would do that. So usually when you're solving these types of problems, it's going to be critical that you determine the initial conditions on the actual component that you're trying to find the voltage across, in this case, the capacitor. And the way that you determine the initial conditions is to actually draw the circuit before the switch is closed. So this is t less than 0. The common way you see this written in circuit books is at t0 minus, so right before the switch is actually open. So right before the switch is open, just draw it as a closed circuit. What's going on here? You got 9 volts, 2 ohms in parallel. On this side, you got a 4 ohm and a capacitor in the series combination of these two is in parallel with the 9 volts. Well, if this thing has been closed forever, remember a capacitor to DC is an open circuit. So this is really what's going on from an analysis point of view. You're measuring the voltage across an open circuit with that capacitor removed. Well, if this is an open circuit, there's going to be no current down this branch. If there's no current down this branch, there's going to be no voltage drop across this resistor. That means if relative to the reference, there's 9 volts at this node, if there's no drop, there's 9 volts at this node relative to the reference. VC is actually 9 volts here. So there's 9 volts across the resistor, and there's 9 volts totally across the actual capacitor, because the capacitor is acting like an open circuit. Well, what's going to happen right at the second that that switch opens? Well, the voltage source is actually going to go away. If you notice, it's not drawn at all in this circuit. However, in addition, remember that at that time, immediately when the switch is open, t equals 0 plus, the voltage across the capacitor is going to have to be 9 volts. Why? Well, when you think about the rule that governs the IV relationship for a capacitor, it's I equals C dV dt. And remember last time we said anything that's in the derivative can't change instantaneously. So if it was 9 volts before the switch opened, it's 9 volts after. So that gives you your actual initial condition. So remember that in a source-free circuit, the initial condition goes right in the front. So it's that 9 volts that is going to be decaying exponentially. How is it going to be decaying? Well, in this circuit, the equivalent resistance is 4 plus 2, or 6. When you find the actual R times C product, which we'll eventually call the time constant, for a circuit with only one capacitor or one inductor, if you got multiple resistors, all that you do is you find the equivalent resistance. So 4 plus 2 is 6. 6 times 10 is going to be 60 microseconds for the product of R times C. So the way that this circuit is going to work is it's going to have the 9 initial volts decaying exponentially with a time constant of 60 microseconds. We want to define it at 200 microseconds. When you plug in 200, that's just going to be basically 20 divided by 6, or like 3 and change. And if you put that in a calculator, you'll get 0.321 volts. So that's decayed all the way from 9 volts almost down to 0 in 200 microseconds. It doesn't matter that it's 200 microseconds. It matters that it's multiples of 60 microseconds. It's like 3 time constants. And what we're going to see is, for all practical purposes, after 3 time constants, all of the initial decay is done. After 5, you're practically at 0. So hopefully that served as a good introduction, and I'll see you all in the next video.